In Chapter 10, my favorite chapter, we're going to be talking about a really powerful transformation called the Laplace Transform. It's probably the topic that you will use the most in your other classes that have applications, so physics, engineering, topics like that. And in this chapter, we're going to be solving differential equations of the form y double prime plus ay prime plus by equals some forcing function f, because Laplace transforms can handle a wide variety of forcing functions, including, which is really cool, instantaneous forcing functions, such as a hammer being, we did spring mass a little bit ago, a hammer being affecting the mass at the end of a spring, or even intermittent, a hammer coming down at a certain frequency onto a system. So Laplace transforms are really, really powerful. Let's start with the definition. So the definition of the Laplace transform, we need to establish that f is defined on the interval 0 to infinity. Then the Laplace transform of f, we usually use a script L or a capital F of S, is given by the following formula. It's the integral from 0 to infinity of e to the negative st times f of t dt. Now you might look at that and wonder how in the world that could make things easier for us. The Laplace transform is a special case of something you may have heard of called the Fourier transform, and I'll post some videos to our class so that you can kind of on your own time explore what each of these are visually. But I'm going to tell you simply here, the point of the Laplace transform in our class in differential equations is the Laplace transform changes differential equations into, believe it or not, algebraic equations. That is amazing. So our Laplace transforms are going to change this differential equation up here into an algebraic equation that we can solve much more easily than that. So the main idea in 10.1 is to explore some common functions and what their Laplace transforms are, and see why we get the results we get, and then to try a couple of Laplace transforms on harder functions. We're not going to get to solve a differential equation in 10.1, but don't worry, that's coming soon. So let's start with some basic functions that we should all know the Laplace transform of. Okay, so I wanted to keep our definition up here, so I'll highlight this definition in yellow so we can refer back to it as we go through. And then on the right-hand side of the page, you'll notice I have the Laplace of a variety of functions. And there's some really basic functions. We're going to start with just taking the Laplace of a constant, then the Laplace of an exponent on a variable t, so t to the n, then e to the at, then cosine of bt and sine of bt. And I want to point out in the definition, the Laplace of little f is equal to capital F of s. This capital F of s is going to be our algebraic formula in terms of s. So watch what happens for the first one. Let's find the Laplace for f of t equals 7 pi. So a constant. Okay, so here's what we're going to do. the Laplace of 7 pi is equal to the integral from 0 to infinity e to the negative st times 7 pi dt. Okay, so now remember, when we're integrating this, t is the variable as far as the integral is concerned. S, while it's a variable in nature, s isn't varying over this integral right here. So s is behaving like a constant, and certainly 7 pi is. Now, one of the reasons, admittedly, that I love Laplace transforms is I love teaching calculus too. So integrating an improper integral from 0 to infinity is cool. So here's how I'm going to write that. This is the limit as, let's say, b goes to infinity of the integral 0 to b of 7 pi e to the negative st dt. Okay. Then, we don't need the 7 pi in there, and the integral of e to the negative st is just a quick u sub. So without too much trouble, we should get the limit as b goes to infinity of negative 7 pi over s e to the negative st from 0 to b. Okay, so plugging in b and plugging in 0, we have the limit as b goes to infinity of negative 7 pi over s times the quantity e to the negative s times b minus, e to the 0 is just going to be 1. But as b goes to infinity, remember, e to the negative sb really is 1 over e to the sb. And as b goes to infinity, this is going to 0. So we have negative 7 pi over s times negative 1. In other words, we have 7 pi over s. Okay, so our Laplace transform of 7 pi is 7 pi over s. Notice it's an algebraic function of s. Okay, so without doing this all over again, the Laplace transform of any constant is that constant divided by s. Okay, I would like to do the first 4 of these and then just talk about, I don't need to do the sine one and the cosine one, I'll talk about how you can see the results from, just if you look at one from the other one. So let's do t to the n. And let's specifically do n equals 2. So let's find the Laplace transform for f of t equals t squared. Okay, so that would be the Laplace transform of t squared would be the integral from 0 to infinity e to the negative st times t squared dt. But that is the limit as the b goes to infinity of, 0 to b t squared e to the negative st dt. And this needs integration by parts twice. So I'm going to do the tabular method. We've got t squared 2t 2 and 0 for our u. And our dv, we have e to the negative st. Antiderivative with respect to t is negative e to the negative st over s. I'm going to move these down so they match up a little bit better. Antiderivative of that is positive e to the negative st over s squared. And then his antiderivative is negative e to the negative st over s cubed. Great. So we have plus, minus, plus. So we have the limit as b goes to infinity of the quantity negative t squared. I'm going to write it, the e to the negative st's in the denominator. So s e to the st. Makes my limit a little easier to do. And then another negative 2t over s squared e to the negative st. And I'm going to erase my integration by parts, but I'm going to get a third negative 2 over, let's see, s cubed e to the negative st. Now I'll erase all this work here. So 2 over s cubed e to the negative st, and we're integrating from 0 to b. Okay. Oh. S negative st's, they're already in the denominator. Those are positive. Okay. Limit as b approaches 0 of infinity of, let's see, this is negative b squared over s e to the st minus 2b over s squared. Oh my gosh. That's sb, not st. So careful to not write a negative. E to the sb. So negative b squared over s e to the sb minus 2b over s squared e to the sb minus 2 over s cubed e to the sb plus, because we'll have minus and negative, well, this will be 0. The next term will be 0, but the last term will be 2 over s cubed times 1. So this last term, when we plug in t equals 0, this is the only portion that'll go to 1, and everything else is fine. The first two terms go to 0. Okay, limit time. As b goes to infinity, you could use L'Hopital's rule, but a polynomial is far less powerful than an exponential function. And remember, as far as this limit is concerned, the s's are being held constant. So all of these first three terms, as b goes to infinity, the denominator overtakes the numerator quickly, and they all go to 0. But this last term here, 2 over s cubed, it doesn't have any b's in it at all. So now it's the limit of a constant. So we have 2 over s cubed. Okay, so let's see. That was the Laplace transform of t to the 2, is 2 over s to the third. So here's how it is in general. The Laplace transform of t to the n is n factorial, so this is really a 2 times 1, over s to the n plus 1. Okay, let's do e to the at now. So the Laplace transform of e to the at is the integral from 0 to infinity e to the negative st times e to the at dt. Well, thankfully, they both have base e. So since t is the variable, I'm going to write this. This is the limit, just like before. B goes to infinity of the integral 0 to b e to the a minus s times t, because a minus s will just be a constant when we integrate. So that will give us the limit. B goes to infinity of the quantity e to the a minus st divided by a minus s from 0 to b. All right, plug in the b and the 0, and we have e to the a minus s times b all over a minus s minus, oh, when t equals 0, this is 1 over a minus s. Now, I'd like to rewrite this one more time because I want to make a point about a and s. Whether a or s are bigger, which one is bigger between a and s, will determine whether this exponential goes to the bottom, the denominator here, and thus the whole term goes to 0, or stays in the numerator and this limit becomes infinite. So let me rewrite this so we can discuss it a little bit more clearly. This is the limit as b goes to infinity of 1 over a minus s e to the s minus a times b minus 1 over a minus s. Okay, so this first term will go to 0 as long as s minus a is positive. In other words, as long as s is bigger than a. But remember that ultimately a is always a constant. A is the coefficient of the t in the exponential. S, however, is ultimately a variable. So we can determine that s is bigger than a. We can declare that s is bigger than a. And if s is bigger than a, this limit in the first term goes to 0. So we could say that's true for s's are bigger than a. So when you see these results, you might see for this one the condition that s is eventually bigger than a. And that's okay, just as a reminder, because a is a constant. A is a fixed constant, but s can vary. So as long as s gets eventually big enough, then we're fine. Okay, well if that's true, if we can make that stipulation that s is bigger than a, so that s minus a is positive, then we have just this as our result. And I'm going to rewrite negative 1 over a minus s as 1 over s minus a. So the Laplace transform of e to the at is 1 over s minus a. Okay, now for the cosine. Now, admittedly, cosine of bt is the most intensive algebra one. I'm probably not going to be able to fit this on this page, but I'll do my best. So here we go. Let's find the Laplace of cosine, which is the integral 0 to infinity e to the negative st cosine bt dt. Okay, so that will be the limit as b goes to infinity, the integral 0 to b e to the negative st cosine bt dt. Okay, this requires integration by parts a couple of times, and if you remember Calculus 2, you probably had an integral just like that one on your integration test. So let's kind of go aside here in green and just talk about the integral of e to the negative st cosine bt as an aside, so we don't have to keep writing in the limit sign. Okay, so integration by parts. Let's see, when I did this one, I chose my u to be cosine and the dv to be e to the negative st dt. Doesn't matter which one you choose, I just picked this one. So du is negative b sine bt dt, and v is negative e to the negative st over s. So first round of that integration is negative e to the negative st cosine bt over s minus, we have minus the integral, and there will be 1, 2, 3 negatives total. So minus the integral of, I'm going to factor out the b over s, and then we have e to the negative st sine of bt dt. Okay, which we need to do integration by parts one more time. So if you're doing these with integration by parts, it's a good idea if you picked u to be the trig function in the first round continue to do so. So I'm going to pick, it isn't mandatory, but it can sometimes backfire. I'm going to pick u to be sine of bt, and dv is e to the negative st dt. So du is b cosine bt, and v is negative e to the negative st over s. Okay, so let me scooch this up just a bit. I think we're actually doing pretty good on space. So we have, don't forget, we're integrating e to the negative st cosine bt. And we first got e to the negative e to the negative st cosine of bt over s minus this, and I can't forget to multiply by negative b over s. So negative will be positive. B e to the negative st sine of bt, but over s and the extra s, so over s squared. Okay. Again, we have minus the next integral, so the minus from the formula, the minus from the distributing the negative, b over s through, and a third minus from the v, so we'll have three negatives, make that a negative integral. Let's see, looks like we have some constants. So we've got two b's and two s's to pull out. B over s from the coefficient in front of the integral, b in front of the coefficient in the cosine, and s the coefficient of the e. So negative b squared over s squared times the integral, again, of e to the negative st cosine bt dt. Okay. It's really important to notice that we just got the same integrand, e to the negative st cosine bt, that we were starting with. So what we do in true slimy form is we're going to add that to both sides. So we have one integral e to the negative st cosine bt plus the b squared plus over s squared e to the negative st cosine bt dt. So we have 1 plus b squared over s squared times that integral, e to the negative st cosine bt. And moving up a little bit more, we have this, the negative e to the negative st cosine bt over s, and the positive b over e to the negative st sine bt over s squared. Okay, for both the 1 plus b squared over s squared and for the entire right-hand side of these two fractions, I'm going to combine the fractions now. So this will give me s squared plus b squared over s squared times the integral e to the negative st cosine of bt dt, and equals negative s e to the negative st cosine of bt over s squared, and b e to the negative st sine of bt over s squared. Cool. So those s squareds are going to cancel when we flip and multiply, and we're going to end up with the integral of e to the negative st cosine of bt dt is equal to 1 over s squared plus b squared times the quantity negative s e to the negative st cosine of bt plus b e to the negative st sine bt. Super cool. Okay, let's go back to blue for what we were looking for. For this integral, we were looking for his limit as b. Oh, I don't want b. Let's change this b in the limit to be c. Way back up here. Yeah, there we go. Can't have that many b's floating around the same problem. So I'll make this c. Okay, so we're taking the limit and then, oh, that was up here too. There we go. C. Okay, so we're taking the limit as c goes to infinity of the integral from 0 to c of our to the negative st cosine bt dt. So that's the limit. I think I can fit this here. As c goes to infinity of 1 over s squared plus b squared times negative s e to the negative st cosine t. Oh, make that cosine bt. And plus b e to the negative st sine bt as we integrate from 0 to c. Okay, let me write this in. Limit as c goes to infinity of 1 over s squared plus b squared times this. Okay, I'm going to put the e to the negative st's in denominators. So we have negative s cosine bc over e to the sc plus b sine bc over e to the sc minus, well, actually minus a negative, so plus, e to the 0 is 1, so s times 1, and cosine of 0 is 1. So I have s times cosine of 0, which is 1, over e to the 0, which is 1, plus b sine of 0, which is going to be 0, over 1. Okay. Love this is going to 0. This is just s. That'll stay. And then this cosine and sine mess over here. So remember, your c is what the limit is carrying to infinity. E to the sc in each denominator here is increasing without bound. But both sine and cosine are bounded between negative 1 and 1. So clearly the denominator gets bigger than the numerator, and both of those limits have to go to 0. Both of them do. You showed this in Calculus 2 by using the Squeeze Theorem. But once you get past Calculus 2, I'm just going to say it. So since our cosine and our sine and our numerators are bounded between negative 1 and the biggest they could possibly get is 1, then yes, they're oscillating back and forth, but man, that e in the denominator is getting so darn big as c goes to infinity that it doesn't matter what the numerators are oscillating if they're only getting to 1. So here's what we have. We have s over s squared plus b squared. Cool. Okay, so this was the cosine one. Before I scroll back up and write the result, I want to take this opportunity to talk about what happens in the sine. So if you change the cosine bt to sine bt, then what happens is your cosine and your sines are mixed up here, meaning the sine is being multiplied by the b I'm sorry, the sine is being multiplied by the s, and the cosine is being multiplied by the b. So at this part down here where we plugged in 0, we plugged in c first, and the same stuff that I have here in yellow about using the squeeze theorem, these two first fractions go to 0, always. But what happens when you have the sine is instead of having s times cosine, you have s times sine, and then you have b times cosine. So it's the s term that goes to 0 and the b term that stays. So for sine, you don't have s over s squared plus b squared. You have b over s squared plus b squared. Okay, so let me scroll back up, write those results there, and then we'll encapsulate that on the next page. So the cosine one is s over s squared plus b squared, whereas the sine one is b, so the coefficient, over s squared plus b squared. Okay, as far as your homework goes and quizzes and tests, you could be asked to verify any one of these 5 using the formal definition of the Laplace transform. For the next example, I just want to use the Laplace transform. So let's try an example. And before we do that example, I want to point something out that is crucial to Laplace transforms. I've got the definition of what the Laplace transform of a generic function f is, and I want you to notice this. The Laplace transform of a sum of 2 functions, f plus g, would be defined to be the integral from 0 to infinity of e to the negative st times the quantity f plus g dt. But that would just be the integral 0 to infinity of e to the st f of t dt plus the integral from 0 to infinity e to the negative st times g of t dt, which is the Laplace of f plus the Laplace of g. Cool. You probably know what I'm going to do next. The Laplace of a constant times a function would be the integral 0 to infinity e to the negative st times the constant times that function, which you can of course factor out to be the constant times the integral, e to the negative st times f of t dt, which is the constant factored out of the Laplace transform. And that means that the Laplace transform is a linear transformation. Super cool. Okay, now we can do an example. So for this next example, let's find the Laplace transform for f of t is given by 3 e to the negative 2t plus 7t to the 4th minus 6 plus 2 sine of 3t. What this will be when we start solving differential equations is a forcing function. A rather ugly forcing function I would not want to use variation of parameters or annihilators on. A really ugly forcing function. So let's get started. The Laplace of this f. Okay, let's use our chart over here. E to the negative 2t. So that means that's this third one down where a is negative 2. And remember, Laplace transforms are linear transformations, so the 3 can just get multiplied to whatever the Laplace transform is, factored out of it. So this would be 1 over s minus a, but s minus negative 2 is 1 over s plus 2. Okay, likewise for the 7t to the 4th, just going to multiply the 7 by whatever the Laplace transform is of t to the 4. That would be our second one we have listed. So t to the n is n factorial. So that would be 4 factorial over s to the n plus 1, s to the 5. Oh, first time I taught differential equations, one of my students said, "Can you not put any problems with s's and 5's in the same problem?" And I was a rookie that time, and I foolishly said, "Sure, I'll do my best." Yeah, that's not going to happen. It's too common of a number, and s's are everywhere, so be really careful. In fact, I'll make a point to go back, and I'll erase, and I'll make my 5 very 5-like. There we go. Okay. -6. 6 is a constant, so this will be 6 over s. And 2 sine of 3t will be 2 times, okay, so here's the sine. Now sine is the one that has the coefficient in the numerator. Cosine is the one that has just s in the numerator. So the coefficient for sine of 3t is 3. So 2 times 3 over s squared plus the coefficient squared. So 3 squared is 9. Okay. So that's fine for our Laplace transform. If you want to clean it up and write the Laplace transform as 3 over s plus 2, I would just leave this as 7 times 4 factorial. Don't worry about writing 4 factorial out. Over s to the 5th minus 6 over s plus 6 over s squared plus 9. Cool. Okay, we're going to get lots of practice with finding those Laplace transforms, so I'm not going to do another example quite that easy. I would like to finish with a Laplace transform of a continuous, or of the piecewise continuous function. So let me show you what that looks like. So before we jump into this last example, I want us to sketch this graph. I want us to sketch f of t is given by 2 when t is between 0 and 5. It is including 0 but not 5. When f of t is 0 when t is between 5 and 10. It includes neither 5 nor 10. And e to the 4t when t is bigger than 10. Okay, so here's what that looks like. Let me draw some x and y axes in there. And let's get started. Okay, so t goes 0 to 5. It's equal to 2. The f of x is equal to, f of t is equal to 2. So we have a closed circle at 0. Here's 5. We have an open circle at 5, horizontal line. Okay. It's equal to 0 between 5 and 10. So, and they're not inclusive. So the 5 and the 10 both have open circles. And then t is bigger than 10, e to the 4t. You know what? E to the 40, did you know that that's right here? It is. It's right there. Open circle going up. You know, I would like to just at least put 1 in. If it's an equals 2, you make it a closed circle, or you can actually not even write the closed dot in, just for the sake of showing you. Okay, when we're finding the Laplace transform, we do need to have what we call piecewise continuous. So this f is what we call piecewise, which I can't spell, piecewise continuous, meaning it has a finite number of what we call jump discontinuities. So it has a discontinuity at 5 and at 10, but they are what we call jump discontinuities. They're not asymptotes. That asymptote would not be a jump discontinuity. It just simply goes from one value to the next value at a jump. So as long as we have a piecewise continuous function, then we can take the Laplace transform of that function. So here's how we're going to do that. The Laplace transform of f, you already know, is the integral 0 to infinity e to the negative st times f dt. However, f is at first on 0 to 5 defined to be 2. And if you remember your integrals, you can set these up even if you have not defined, the function not defined right at 5, you can still set the integral up. Middle integral is terrific. It's the integral from 5 to 10 of e to the negative st times 0 dt. And the final integral is the integral from 0 to infinity of e to the negative st times e to the 4t dt. Now the reason that I don't have my chart up like I did for, sorry, this is part B, for the previous example is because I'm finding the Laplace transform, but I can't use the chart like I did because none of these integrals are going from 0 to infinity at all. So I can't just go back to what we just came up with. Even this integral, which at least is going to infinity, it's starting at 10. So I can't use the formulas that we did. But I still know how to integrate, so I can still calculate this. So this first one is going to give me, let's see, negative 1 over s comes out. So I have a negative 2 over s times e to the negative st from 0 to 5. Then I have a big fat 0, and then the limit as b goes to infinity of the integral 10 to b e to the 4 minus s times t dt. Okay, let me scooch this up and plug these in. So the first one, negative 2 over s times the quantity e to the negative 5 s, let's make that more 5-ish, 5s, minus 1. And then the last integral, the limit as b goes to infinity. Let's see. Oh, we've done stuff like that. So this is e to the 4 minus st divided by 4 minus s from 10 to b. So I'll plug in b and plug in 10. And when I rewrite my first expression, how about we make this 2/3 times 1 minus e to the negative 5s. Okay, plus the limit as b goes to infinity of e to the 4 minus s times b over 4 minus s minus e to the 4 minus s times 10 over 4 minus s. Okay. But remember, s is varying and 4 is fixed, so as long as s is bigger than 4, this first limit goes to 0 because this exponent will be negative, pushing it to the denominator, making the limit get tiny without bound. So here's what we've got. 2/3, 1 minus e to the negative 5s. I'll write this plus e to the negative 10s plus 40 over s minus 4. Okay. It might not be the prettiest function you've ever seen, but you know what? We just took the Laplace transform of a rather ugly forcing function because it was piecewise in nature. That's really powerful. So in the next section, we'll get closer to solving some differential equations with these.